So we kind of checked this guy out in the individual practice today, but we're going to be looking at it again. And really, if you were like kind of confused about what happened in the independent practice today, pay close attention. If not, you can skip ahead and figure out where we're actually going to start notes today, which will be down here at this topic 2.3. So the very first guy here, it says find the slope of the tangent line to the hyperbola y equals 2 over x at x equals 3. So when I look right here, I know that x is approaching a, and I know that I have f of x, which is just going to be my original function, and then I have f of a. This a value, or what we're approaching, is actually going to be that 3. So I'm going to rewrite this here, and I'm going to say the limit as x approaches 3. Now I'm going to plug in that f of x, which is 2 over x, and I'm going to subtract f of 3, right? Because I'm saying as we're approaching 3, so I'm plugging in 3 for a. A is that substitution, 3 is that substitution for a. So I'm going to subtract 2/3. Every time I see an a, I'm plugging in a 3, and that's going to be an x minus 3. Now we need to get a common denominator here. So I'm going to get a common denominator in this numerator, and I'm going to say, okay, let's get a common denominator of 3x. So I'm going to be multiplying these first two numbers by 3 over 3, and then the second two by x over x. And what that gives us is we can rewrite as the limit as x approaches 3 of 6 minus 2x over 3x. We're dividing by x minus 3, so I'm just going to write that horizontally. Remember that I can always rewrite this. When we're dividing, I'm going to flip and multiply by a fraction, so instead of dividing by x minus 3, I'm going to multiply by 1 over x minus 3. Now at this point, we kind of talked about this a little bit in your homework review when we looked at things. And we said, all right, if I'm checking this out, I know I factor a 2 out of this numerator, and I'm left with a 3 minus x. That almost looks like x minus 3, but not quite. So I'm actually going to take it one step further, and instead of factoring a positive 2 out, I'm going to factor a negative 2, and that's going to flip those signs. So I'm going to rewrite it as the limit as x approaches 3 of negative 2 times. We have a negative 3 and a positive x, so I'm just going to write this as an x minus 3 times 1 over x minus 3. And the reason I did that is because I'm trying to cancel as much out as possible. At this point, we're going to rewrite this as the limit as x approaches 3 of negative 2 over 3x. And then remember that we are just substituting when possible. So at this point, I would just plug in the 3, and then I can say m, or my slope, is going to be negative 2/9. My slope is negative 2/9 at x equals 3. So with that 3 substituted, negative 2/9. Let's keep on going here. If I'm using the formal definition, so I'm actually looking for an equation, right? You would normally say, okay, I'm going to be plugging in like an a plus h or an x plus h. But since we have a defined value, we said, okay, x is 3, or that a value is 3. So I'm going to rewrite this as a 3 and a 3. And then we're going to start plugging things in. I know that what this looks like, remember my function is 2 over x, and that x is being substituted first with a 3 plus h, and then second with a 3. So I'm going to rewrite this as the limit as h approaches 0 of 2 over 3 plus h, because remember I'm just substituting that input into that x value, minus 2/3 all over h. Same thing that we did before, we need a common denominator. So I'm going to be multiplying this first term by 3 over 3, and the second term by 3 plus h over 3 plus h. I'm going to ignore that denominator of h here for a second, and let's just get that written out. Got a little aggressive there. Once I do that, I get the limit as h approaches 0. I'm going to say equals to show that this is continuous. We keep on working through. And this is going to be 6 minus, distribute that, 6 minus 2h over 3 times 3 plus h, and I'm just going to leave that there. And then once again, I'm just going to rewrite. Instead of dividing by h, I'm going to multiply by 1 over h, right? Because technically, this is h over 1. So when I flip it to multiply, it becomes 1 over h. Moving on to simplify, these 6's cancel out. These h's cancel out. And I'm left with the limit as h approaches 0 of, we have a negative 2 over 3 times 3 plus h. Now I can plug in, and I can say as h approaches 0, after I substitute that in, I get my slope, that's negative 2 over 9. So either way works to find this. Remember, we're finding at a specific value, which is why that x is going away, and we're substituting x for 3. In general form, we would have kept x in the entire time, and then we could have substituted whichever value we wanted in for x. So know that all we're doing here is we're finding it at a specific point instead of saying this is a general form. All right, now we're going to move on to kind of like a new lesson. So hopefully cleaning some of that up, and we're just going to take that and extend. We're going to be finding the slope of a tangent line of a point and just continuing with this idea. So the first thing that I want for us to look at is if you graph y equals sine of x, and let me pull that up on my graph for you. So here I have my calculator pulled up. So I'm going to come in here and plug in sine of x. Remember, we want to see it in radians. So I'm going to go to that, let's go to mode and check out. Great, we're in radians. Now if I click on graph, let's do a zoom 6. There we go. Getting a little bit more standard. So we're going to see, let's zoom in and let's see what's actually happening, or what is the slope of the sine curve as we're getting close to 0. So let's go to zoom in. When I zoom in, okay, let's zoom in some more. Oh, we're getting even better. Once I zoom in really, really close, it's looking like my sine curve all of a sudden turns into a line. And remember to go back to normal, just zoom 6 is that standard. So super, super close. It's looking pretty equivalent. So we're going to say that the slope of that line looks to be about m equals about 1. I'm going to say right here. And we're looking for that at the origin. So what I can say about the tangent line is I can say at x equals 0, the slope of tangent is 1. Or I can say f prime of 0 equals 1. We're saying that prime, remember, that's like the derivative or the slope at that instantaneous rate of change of f of x equals sine of x. So we're naming our functions here. So writing the equation of the tangent line at that point, I know that the slope is 1, but let's also think about how do I write my equation for my tangent lines? You know that a line equation using point slope is y minus y1 equals m times x minus x1. So we're just going to plug in some values. I know that if I were to plug in a 0, right, I know that f prime of 0, or the slope, is going to be 1. I also know that my normal point, if I plug in a 0 into sine of x, sine of 0 is 0. So plugging this into my point slope equation, this is my ordered pair. Remember, we're thinking your ordered pair is 0, 0. So if I have y minus 0 equals 1 times x minus 0, simplifying it down, you just get y equals x. You can also leave it here or simplify it further. We're going to talk about some peculiar tangent lines that occur here. So I'm going to use as straight edge as I can. I'm not the best drawer. Let's see if I can actually use the straight edge on this app. And we're going to get some lines at each of these points to think about what would the tangent be. So here is a tangent line at point A. Here's a tangent line at point B. And then here's a tangent line at point C. So getting these lines in, and if I were to estimate here, you can just use rise over run and count how many points am I going up or over. So I'm going to say here the slope is about 5, the slope is about 0, and I'm going to say here, let's see what, let's go down 2 over 1. My slope is about -2. I'm going to do a sub. Here's at A, here's at B, here's at C, just to keep us clear. Same thing here. On point B, if I just drew a line, you would say, oh, okay, the slope at A is going to be about -2, down 2 over 1, down 2 over 1. At C, we're going to have +2. It's an absolute value function. But at B, I don't really know what's happening here. My slope is not gradually changing. What we have here is this is called a cusp. And a cusp is like a point on your graph. This right here, the slope, so m of b, does not exist. So since I don't have a slope here, we can also say the tangent line does not exist there. Same thing happens here at C. If I'm looking at this, we are coming, let's get that line deleted. If I were looking here, you would have a slope of about, what, like -1/2 at A. My slope at C would be about +1/2, but those slopes we're drastically coming in 2 different directions, and we come towards another cusp. So the slope also does not exist. So m of b does not exist. Same thing happening at this guy right here. At this point, we have a vertical tangent line, and a vertical tangent line has an undefined slope. So I can also say that does not exist. Filling out some quick definitions here. When the curve is concave up, so think about, here's the curve, concave up, the tangent line lies below the curve. When the curve is concave down, the tangent line, where are those tangent lines, right? This is going to be above the curve. At a turning point, so a minimum or maximum, the tangent is 0 or horizontal. So think about this in terms of like acceleration. If you are accelerating, and then you start decelerating, there's at one point where nothing will be happening, and that's that turnaround point. A point of inflection, this is a new term for you guys. A point of inflection is where concavity changes. So that means we're changing from concave down, right, concave down, to concave up. And where that concavity changes, we have this interesting point here where that curve or that tangency is going to be straight up and down, just like we saw in point D. So it's changing from concave up to concave down. They do a little better job in their illustration. And we're going to say that the tangent is vertical or does not exist. At a sharp corner, so a cusp or a corner, that means it's a point or that means it's a cusp, we're going to say the tangent does not exist as well. And then at a point of a linear function, so think about a straight line, the tangent is going to always be the same slope as the line. So for example, if my equation of my line, if I had y equals 2/3 x plus 4, my tangent, regardless of where I go, is just going to be 2/3 because that's always the rate of change that I'm moving at. So the last thing that we're going to be looking at is we're going to estimate the value of the derivative for each value. So g prime, whenever we see this, we're thinking, what is the derivative or that instantaneous rate of change? Then we're going to estimate the slope or that derivative at that point, and also think about like what would the equation of the tangent line be? Now, I wrote the tangent line approximation of f as a function of a. This is not a new formula. Let's look at all these components here. You know that f of x is a y value minus an input. So I said, okay, that's the same thing as like y1. F prime of a is saying like what is the slope at that point? And then you have x minus a, where in this point a is going to be your x1. So all we did is we're using function notation to describe the exact same thing that we have before. So we are going to get 2 examples done, and then we will work on the rest of this in class. So let's get this done. Where a is -3, so we're all looking at -3. Let's go over here. -3 is going to be happening right here. So we're looking at point A. So this is going to be at point A. Now let's get this filled out. The derivative estimate, so we're going to say, okay, what looks like is happening here at point A? If I were to draw a line, let's see. I'm going to actually get this guy a little bit closer so we can kind of get a better idea of what's happening. He is not getting there. And if I look at this guy right here, we're going to say, all right, this looks to be, we're going about 1, 2, 3, 4. So it looks like we're going about down 4 over 1. So I'm going to say my derivative estimate is going to be -4. That point of tangency, or like what point is it going through, is going to be 1, 2, 3, 1, 2, 3. So this is -3, -3. That function behavior here, we're decreasing. And we are concave up. Because the concavity here, remember, we're like a smiley face, concave up. So if I'm plugging in to that y minus y1 equals m times x minus x1, I would get y minus -3 equals m times x minus -3. Let's substitute that m value. That m value would be the slope, and at that point it looks to be our slope is about -4. So I'm just going to rewrite as y plus 3 equals -4 times x plus 3. You do not have to simplify further. That is the equation of the tangent line. Leave it. Let's get one more taken care of. Let's do +3. Point F. Oh, it is not on there. We will do, let's do point D. Let's do point D. That works just fine. So that looks to be about 1.25. Great. Let's do point D here. Estimate of the derivative, so we're saying like what is happening here? That slope is 0. So I'm going to say my estimate of my derivative is 0. The point of tangency, or like where is this 0 occurring, is at 1.25 positive 1. We are at this like turnaround point here. So we're just going to call this a turning point. This is a max. So max, and it is concave down. So now I'm just substituting in. You have y minus 1 equals m, which is our slope, 0, x minus 1.25. Right here, you're like, okay, this is going to all cancel out. You can leave it like this. That's totally fine. Or I can say, if I were to simplify that out, I could just leave it at y equals 1. And you are good to go.